This is the setup on the F1 mill for cutting the 3 ports into the backplate. This is the start position, which shows 3.3 drill in an Albrecht chuck, 1mm clear of the surface and centered on the extreme edge of the backplate. The backplate blank is held in a small 3-jaw Emco chuck on an SL dividing head mounted on a home-built adjustable angle table. It's adjustable from 0 through to 90 in any sort of increment. The holes lock off in at the important angular steps. Just a case now of continuing with the operation. I use just a mist coolant. See the start of the program. Press the start button. The tool has been changed to a 3mm cutter. Now this is going to plunge in on the hole that's already been cut to rough out the first of the 2 side ports. This takes quite a while to do because the length of the cutter dictates that it can only cut at 1.5mm depth on each pass, and it's cut in multiple passes using a sub-program which gives it the shape of the port to within 0.25 of a mil where possible of the edges of the required shape. There's no point in leaving this running because it will probably become a bit boring. I can show you the sub-program which is there. 45 is the start of it. So the first line it moves 340 in X and 130 in Y. Line 46, that's the 25, bringing it back in. So you've got 1, 2, 3, 4. You've got four lines moving. Line 49 is all double O, so it's not doing anything. Line 50 is the M17, which takes it back to the previous line. You'll see now when it hits 49, it'll go straight back up to line 30. And 31 was a G25, which takes it into the sub-program again. There's a G25 in line 14 that you can see, sending the program to line 51, which is the operation. The operation after this, look, where it stops the spindle motor. Moves the tool away, ready for a tool change to changed to tool number 3. We'll pick it up again at that point where it changes to tool number 3. Right, we're back with this now. You can see that the rough shape of the port there, the cutter has been changed to 1.6mm diameter. Now going to put the feed in, turn the air on for the mist coolant going on. Close the door, press the start switch, spindle starts. You can probably just about make out what's happening there. Because it's a 1.6mm cutter, the feed rate is particularly slow, especially on the first 2 passes, until it gets some support of the wall that it's running into. It's not easy to see what's happening there, but I think that you can see that the straight line of the port is beginning to form. It's better without the machine light on, so you can see there that the port is becoming, the shape is becoming apparent. Comes back into this corner and then it'll stop travelling and go down the next 1.5mm. Then it goes through to another sub-program as the roughing out port did, but it's only travelling at 25mm a minute, which is quite slow. So we'll come back to this when that's complete. And here you can see that the head has been indexed round, ready to cut the second boost port, but that's the finished item in the chuck. And we're back to the 3.3 drill. Some coolant on it, there's a bit of mist on it. Close the door. And away it goes. Now it's going to do exactly the same operation for this second port. So we'll close this off. Not much fun watching it a second time. And we'll come back when we start to do some machine the flat for the piston and another detail on the backplate flange. What we've got now is a 6mm 4-flute cutter, and it's in position ready to start cutting the flat on the top of the backplate between the 2 ports, which gives clearance for the piston on its downward stroke. I think from memory the cut depth is 0.8mm, I'm not certain. I'm not absolutely sure on that, but I've run this program so many times that I don't measure anymore. As long as the offsets are accurately set, I'm pretty confident that the part is going to come out to size, or within any required tolerance that there may be. This is going to cut the flat, as you can see. We'll let it keep running because when it's cut this flat, it excuse me, it goes to the back flange and cuts a flat on the flange as a reference for one of the later operations to ensure that the component is correctly mounted in a jig for machining the back out of the back plate to give it some lightening effect. Not actual lightning, but lighten. Reduce the weight thereof. Turn that light out again, you can see, that's better. Far better without the light. When it's got this part done, that's the end of the program. Comes back, goes there. I'll hit the switch to it's being held in 179. So there we are, that's the end of that program. Right, back with you now. We've just changed the tool. I'll put in a 4mm bull nose slot drill, ready to cut the centre slot. Tool's now moving in, coming up, it's getting into position, start position, ready for the, it stopped on the edge, which is the datum for this part of the program. Press the start button, away it goes, moves over, and it's now cutting the third port on the flat part that was milled earlier, which is to direct cooling charge to the underside of the piston. That's the theory. Who knows if it works? Some people have had success with these plates. Others have found no difference in performance. I suppose it's a case of suck it and see. Somewhere out worldwide there are 76 of them. I don't know how many will be used at the World Championships. I know of at least one that's being used on a sub 60 second timed aircraft. Whether it's the back plate that's keeping the performance up, I'm not sure. It's more about, I would think, flying ability, but there we go. So when that's done, that will be the 7th of the batch that I'm now currently making, which there's 6 completed there, 3 more waiting to go in the machine, plus the one there is 7, that will be the 10 done. So we'll come back to this when we start the next operation, which is to reduce the weight by removing material from the well in the back of the back plate. That's all for now then. What you see now is the finished component. You can see the angle of the table, the peg that retains it. You see that the machining of the ports, there's a lot of reflection there, but that's a better shot. Some of the tools that are used on the job. Next operation on the back plate is lightning cuts into the rear aperture. If you remember, this has been bored 24mm diameter by 12 deep. We now want to cut some further recesses in the bottom to just lighten it somewhat. This is the check I use to make sure that it's central to the axis. Just make sure the clock is at 0 as it's rotated in the hole. That looks all okay. You can see that we now set up for operation 1, which is to centre drill the 4 holes in the back plate. Put some air on, some mist, start button, tool, there we go. What it does now is put 4 centre holes into the back plate for the fixings to the rear of the engine. This is just a simple 12.5 move in both directions. The holes are actually forming a 25mm square. Done the 4 centres, it goes back to now to facilitate a tool change. So we'll put the camera down for a bit. You can see that the tool has been changed. I'll press the program again. It's now coming down because that's the tool offset between the 2 tools. It's moving in. It'll get to the point where it wants to drill the hole and start the spindle. And when it does those 4 holes, that's a 2.6mm drill. The 2.5mm screws. And if we drill them accurately, these holes only need to be 2.6. That's the reason for clocking the centre hole, really, because if that's not clocked, if that's a 0.2 of a mil out, it would mean that the screw holes that we're drilling now wouldn't be aligned with the tapped holes in the back plate when it's fitted. That's moving away now to another tool. It's moving up for a tool change. You put your camera down again. Now you can see that the tool's been changed to a 6mm bullnose cutter. Start the program again. It'll move back to the centre of the hole. I always go back to the centre of the hole, and it's coming out now. It's now going in the back, and it's going to cut a 9mm radius. It's now plunging in. It'll end up at 18mm down, so it'll be cutting 6mm of material. It's a bit of a messy operation, this one. You can see there's swarf flying all over the place. I really need more air going in there, but you can hear it's probably this cutter is getting a bit past its best, I would think. The feed rate is not too fast for it, but it's making a little bit of a noise, isn't it? So we'll switch this off for a moment and come back to it. You see now that we've changed the cutter again. What we've got now is a 6mm 4 flute. This is going to profile the outside of the backplate. Always comes back to the centre, you'll notice that. It's doing the full depth in one cut, but it's I'm only using a slow speed. I could send it around quicker, but it takes longer than to deburr it. As it is, just a wipe over with a Grayson block is all it needs. There's hardly any burrs at all from this speed cut. Materials aluminium 6082 T6. It's widely used for this type of application. It's not one of your tip-top materials, but then it's not under any working stress. We'll stop this and come back later. Right, here we are back again. You can see we've had another tool change. This is the engraving tool that engraves the numbers into the back of the back plate, the ID. Because I can only run it at 2000 RPM, this spindle, engraving has to be done at a very slow pace, otherwise it just tends to scratch rather than engrave actually into the material. You can see I keep plenty of air and mist onto it just to keep the thing clear, save the carbide bit picking any of the aluminium up, which would spoil the depth of cut. This will need a file over it when it comes out. It raises it. It doesn't cut it all out cleanly, but just a very fine Swiss file is all it needs. A couple of strokes over, and a Grayson block, and it finishes it off a treat. And that's the last operation in the lathe, in the mill, sorry. Just need some hand cleaning then, to remove any burrs, run a countersink into the backs of those holes just to round them off so the screws seat properly. Make sure it fits into the crankcase jig I have, and get it packed up and sent away to another happy customer. That's all now. For anybody who saw the earlier videos where I was milling a flat on the top of the case flange, here you can now see the reason for it. That's the flat along this point. That's the flat there, along this portion here, which aligns the backplate correctly into the jig, so that when you can't see it from there, but that's the top. You can see the top of the bowl there where the cutter's coming down, and it ensures that the cutaway for the piston and the ports all remain in the correct alignment. Failing to align these correctly at this point would cause problems when the backplate is fitted to the engine. The piston to start with would fail the backplate on when it's trying to get to bottom dead centre. So it's important that these are. Anyway, there's the. You can see the recesses formed in there, and that's the engraving. That hasn't had a file yet, but it's quite fairly visible what's what on it. Another one here. You can see there 774810. You can see a little bit of burring around those holes where the drill comes through. It's only just a case of putting a counterbore on it. That's all for now then.